Hi, friends of the sun. This is a weekly reading group happening every Monday, or you can join us just on Zoom if you want. And today we're talking about a pretty cool paper where the author develops a rather general framework for operating on point clouds and then tries it on molecules. And I think it's pretty cool. He has a very impressive slides in terms of how he visualizes the topics. So I'm sure you'll enjoy this much. Let's go.
I am Sergey Pozdnyakov. I am a PhD student at EPFL. And the first thing I want to say is that I am really grateful for all people who came here and for their interest. Also, I want to thank the organizers for granting me the possibility to present here my paper, which I am really happy to do. So today I will present you the paper called Smooth Exact Rotational Symmetrization for Deep Learning on Point Clouds. And I would like to start with the very basics. Namely, I would like to start with the definition of atomistic machine learning and with the structure of an input object. So atomistic machine learning stands for predicting, more precisely for constructing machine learning techniques to predict various properties of molecules and materials. And it is really important that the structure of input object is a decorated 3D point cloud. So the so-called Born-Oppenheimer approximation is prevalent in our field. So it means that we can completely neglect the spatial extent of atomic nuclei. So each atom is described by just x, y, z coordinates of its position and by a label with a chemical species. So this label tells us if an atom is hydrogen, carbon, oxygen, and so on. So an important observation is that atomistic system is not the only three-dimensional point clouds in this world, as it is illustrated on these slides. So the leftmost picture is LIDAR. It is a sensor that emits some beams, and it collects the information of the surrounding world also in the form of three-dimensional point clouds, as illustrated on this picture in the middle. And such sensors are used, for instance, in autonomous driving. So such sensors are installed in autonomous cars. They produce the representation of the surrounding world in the form of 3D point clouds. And thus, there is a need in deep learning techniques to process such point clouds in order to make it possible for a car to drive without a driver. So as an immediate consequences of this demand, there is a plethora of general purpose point clouds methods that has been developed, and I quickly overview them on these slides. So very, very roughly, these methods can be grouped into four main classes. The first class are so-called multi-view convolutional neural networks. And idea here is very simple. We just project our three-dimensional point cloud on one two-dimensional projections or onto several ones. And next, we apply like standard 2D convolutional neural networks to these projections. The second class of models are so-called voxel-based models. And idea here is that we project our three-dimensional point clouds onto a three-dimensional grid of three-dimensional pixels that are called voxels. And next, we apply some 3D, three-dimensional convolutional neural network. The next class of models, point convolutions, actually generalize the convolution operator from a regular grid of pixels of voxels to irregular arrangements of points in our point cloud. And the final class of models, point-based models, are actually the ones that eliminates the distinction between features and positions of points. Namely, these points just treat the raw XYZ coordinates of points as features and operate with these features. So what is really important here is that this world of general purpose point clouds is much larger than ours. It's much larger than the world of models proposed for atomistic machine learning. And because of this, one can simply make statistical arguments. So the number of professors, the number of PhD students, the number of researchers working in these domains is much larger than in ours. So the number of GPU hours is also much larger. So one can simply make a statistical argument that probably many cool things and many cool ideas have been proposed in this domain. And this immediately raises a question: why don't we borrow these developments and apply them in atomistic modeling? And why instead we keep stewing in our own juice? Why do we still keep inventing and reinventing bicycles? The answer lies in how we use our models. Actually, the most prevalent target is the potential energy of the system, and then the model is already fit and thus is able to accurately predict energy. What we typically do, we compute forces acting on all the atoms as the derivative of this energy with respect to all atomic positions. And next, we conduct simulations such as molecular dynamics, as illustrated on this animation. Because of this usage scenario, there are quite challenging requirement for a model to be used in practice. Namely, most practitioners in the field believe that the model is applicable only if it rigorously fulfills the following physical constraints. Actually, the model must be smooth and rigorously invariant with respect to permutations of identical items, translations, and rotations. Also, one can say that most practitioners in the field believe that invariant model with moderate accuracy is preferable over not invariant model, even if it has an excellent accuracy. So this challenging requirement of physical constraints actually alienates our domain from our domains involving three-dimensional point clouds and hinders borrowing the ideas, layers, and maybe entire models to apply them to atomistic modeling. This situation is summarized on this slide. So there is a relatively small number of models developed for atomistic applications such as maze, SNET, TensorNet. And these models rigorously incorporate all the mentioned physical constraints into the architecture. And there is a much larger number of models proposed for generic point clouds. And because of the reasons I just have mentioned, it is barely possible, at least most practitioners think that it is barely possible to apply these models to atomistic modeling. So it is really pity, isn't it? Actually, if we carefully investigate the lay of the land in general purpose point clouds models, we can discover that it appears that already out of the box, most of these models, such as PointNet++, are already invariant with respect to permutations, are already out of the box invariant with respect to translations. Most of the models are not smooth out of the box, but typically smoothness is something which is very easy to ensure. The typical source of not smoothness is, for instance, the usage of activations functions such as ReLU, which is not smooth, which is not differentiable at 0. And if we observe such the source of lack of smoothness, it is really easy to fix. Instead of ReLU, we just apply GLU and a piece of cake, snap of fingers, smoothness is ensured. The situation with rotational invariance is much more complicated. So most of the models, most of the general purpose point clouds models are not invariant with respect to rotations. And it is really hard to make them invariant with respect to rotations. Thus, summing up, the lack of rotational invariance is the only obstacle to use all the developments done for the hour domains for atomistic modeling. And now I come to the main contribution of our paper. So our main contribution is a general method that enforces rotational equivariance for any backbone architecture while preserving all the other constraints and smoothness in particular. So now I go to the second part of my talk, which is the actual definition of our method, which is called equivariant coordinate system ensemble. So the first thing I have to say is that I will stick to so-called additive ansatz. So idea is that energy is an extensive property, and as direct consequences, most of the models in atomistic modeling decompose the total energy into the sum of atomic contributions. And next, these atomic contributions are summed up into the total energy. Each atomic contribution is given by some function, which is represented by our neural network or any other machine learning methods, which is called here backbone architecture. And so each atomic energy is produced by our backbone architecture as a function of local atomic environment. The atomic environment is all the neighbors within some cutoff radius. So now imagine that our backbone architecture is not invariant with respect to rotations. So how do we still can produce predictions that are invariant with respect to rotations? What should we do? Actually, it is quite straightforward. So what should we do is that we should define somehow a local coordinate system which is rigidly attached to our atomic environment. Next, if we have such local coordinate system, we can project our atomic environment onto this local coordinate system. And next, we can feed the result to our backbone architecture, which in turn produces us the energy associated with this central atom. So now, if our atomic environment rotates, our local coordinate system, which is rigidly attached to our atomic environments, rotates synchronously with our atomic environments, which means that the projection of our atomic environments onto this local coordinate system stays the same, and so is the final prediction, which is illustrated on this animation. So now the question is how do we define such a local coordinate system? At the first glance, it is not so complicated task. And for instance, what we can do is just to select a pair of neighbors which are the most close to the central atom. And next, we can define a coordinate system for this pair of atoms. It is actually not rocket science how we define a coordinate system given a triplet of non-collinear items. We just need to compute two displacement vectors, normalize them, compute a couple of vector products, and it is done. So problem is solved, done, easy. Unfortunately, no. Life is not so easy, and actually we have to think what happens if atoms move a bit. Namely, imagine that the green atom moves away from the central atom and the yellow atom moves towards the central atom. At some moment, the distance between excuse me, central atom, and yellow one will become smaller compared to the distance between central atom and the green one. So when this happens, there will be a discontinuous switch from a coordinate system defined by blue and green neighbors to a coordinate system defined by blue and yellow atoms. And this moment will introduce a gap in predictions. So this situation is illustrated by this animation. So what we have atomic environment, we have a pair of closest neighbors and a central atom. We have a coordinate system constructed by these closest pairs of neighbors. We have a projected atomic environment to this coordinate system. We feed this atomic environment to a backbone architecture. It produces some target, which is now this value. And the last panel is the static plot, is dependence on of the target on the time, and time is marked by a vertical line. So now we can run the simulation. So during the simulation, actually what we observe is that the green atoms goes away, red atom goes towards, and at some moment in between, there is a discontinuous switch from a green coordinate system to the red coordinate system. And this discontinuous switch immediately causes that the immediate input to our backbone architecture also changes in a discontinuous manner. So this input, like maybe we can pay attention to here, actually changes in a discontinuous manner. So even despite the fact that our backbone architecture is smooth, the like overall computational pipeline after the symmetrization is not smooth, which is especially clear on the static plot. As you can see, there is a discontinuity of the zero order. So touch a knife approach actually indeed helps us to enforce rotational invariance or equivariance, but it sacrifices smoothness, and that is not what we really want to do. Do you have any question?
No, I'm good.
Okay. So now I can proceed, and actually I can proceed to the definition of our method that enforces rotational invariance and preserving smoothness of a backbone architecture. And the core idea of our methods is to use all local coordinate system instead of singling some out. So basically what we do is that if we have atomic environment, we define a local coordinate system for each ordered pair of neighbors. For instance, for this atomic environment, there are 4 neighbors. So in total, there is 4 multiplied by 3 is 12 ordered pairs of neighbors. So in total, we define 12 local coordinate system. Next, we project our atomic environment onto each of them. Next, we fit the result to our backbone architecture. And next, we get our final prediction as the average of all the predictions. So now there is no longer this problem of jumping from one coordinate system to another one, but there are still a few sources of discontinuities which are illustrated here. So first of all, imagine that there is some new atom which flies from outside the cutoff sphere, and at some moment it actually intersects the cutoff sphere and appears inside the cutoff sphere. So when this happens, this atom actually yields a bunch of new terms into the summation here in a discontinuous manner. And so there is once again a gap in predictions at this event. The second problem is actually the situation that sometimes some pair of neighbors can become collinear with a central atom, as illustrated here. And if you have a situation like this, we cannot define a coordinate system for a triplet of collinear points.
Oh, then I think we have a question. Let's go with
Yes.
Yes. Hi. Hi, Sergey.
Yes.
Very cool talk. I just wanted to elaborate two things. First, the rotation operator is it an affine rotation or just rotation?
I agree, but
it's not from my side, the voice.
What is an affine rotation? A rotation with a translation?
Yes, yes. I meant that.
Wait, are you asking what is R here or what?
Yeah, I asked if R includes not only rotation but also translation, because like how I understand it, this is basically a conjugation, right? So we go from one like coordinate system to the other local coordinate system and then back. And no?
This is only rotation, and so basically I defined the backbone architecture to be already translationally invariant, which is, as I presented on one of the previous slides, is already out of the box for most of the architectures, and I only symmetrize with respect to rotations. So R is basically the operator. So R, J, G prime. So J and G prime are indices that runs over the pairs of neighbors. So J is the first neighbor, G prime is the second neighbor, and R, J, G prime is the operator that rotates atomic environments to the coordinate system defined by neighbors J and G prime.
Yes, thank you. And the second question, just to understand complexity of the system, here you show us one local environment, one local atomistic environment. But if you have some large material and you have many central atoms, then how will grow the number of local reference frames that we are considering?
For local models, it's a very good question. So for local models, the symmetrization protocol is applied independently for each atomic environment.
Meaning that we kind of like discretize the environment, and in each sub-environment we compute it separately, or you mean once for the whole material, once for the whole simulation?
So basically, probably I can go back.
Yes.
So basically, we decompose our energy as the sum of atomic contribution. So each atomic contribution is some function of local atomic environment. And so basically, we symmetrize these contributions independently. So when we compute the symmetrized predictions for this atom, we use some bunch of local coordinate system, and we use this local coordinate system only in order to compute the prediction associated with this atom. Next, when we will have to compute the atomic energy associated with this atom as the central one, the calculation will be absolutely independent, and it will rely on its own local coordinate systems.
I see. Thank you.
Yes, thank you for the question.
Okay, I didn't follow all of that. So can you go to the slide? Yeah, the one you're pointing at right now.
This one?
Yeah, so for every local environment, every atomic environment, we now have, let's see, 5 minutes. So n, if we have k neighbors, we have k minus 1 frames that we have to sum over.
Yes, this is also a very good question. Basically, I have a dedicated slides for this, and I will address this just a few minutes later.
Good.
But yes. Yeah, so basically I can proceed. So I stopped at the moment that there are still a few sources of discontinuity, and actually it is possible to solve this problem by a single mechanism by introducing weighting. So basically what we do is that instead of the plain average, we use the weighted average. So we introduce a weight associated with each local coordinate system. And next, so basically, instead of doing the plane average, we do a weighted average with these weights. These weights are constructed out of two stitching functions, which looks like this. And let me explain how these weights fix the previously mentioned discontinuities. Now, so imagine that there is atom which flies from outside the cutoff sphere to inside the cutoff sphere. And now when this atom intersects the cutoff sphere, it exactly similarly as before introduces a bunch of new terms into the summation here. But now, because of this stitching function, which is actually 0 at the cutoff, all the weights for these new terms will be exactly 0. And next, when this atom continues to move inside the cutoff sphere towards the central atom, the corresponding coordinate system will be gradually and smoothly turned on in accordance to this stitching function. And as for the second problem regarding the impossibility to construct a coordinate system for exactly collinear triplet of atoms, the story is exactly the same. Actually, the problematic pairs of neighbors are also zeroed out, and this is done by the stitching function. And on the horizontal axis, there is the vector product between two displacement vectors. So if the vector product is 0 or close to 0, there is no weight. Weight is also 0. And also, we do not face the necessity to define a coordinate system for this problematic pair of neighbors. So this actually concludes the definition of our symmetrization protocol. And actually, from like mathematical point of view, everything is here. Okay, almost everything. But okay, almost everything is here. But as Hannes make a very right remark, from practical point of view, this is an absolute catastrophe. Namely, if we have n neighbors in our atomic environments, this naive application of the discussed version of symmetrization protocol would entail n squared runs of a backbone architecture, which is, I would say, a catastrophic computational overhead. And the question is, can we do better? And the answer is yes, we can do better. And the obvious idea is that there is no reason why we should use the same cutoff radius for both backbone architecture and for symmetrization protocol. So what we can do, we can introduce two different cutoff radiuses. One, the big one for a backbone architecture, and second one, small one for a symmetrization protocol. So this is already very good. This is already quite a significant optimization over the first formulation. But the good thing is that we can do even better than this. So what we can do is that we can introduce an adaptive cutoff. So that's instead of being a global user-specified constant, we can have some function. So our cutoff is a function which depends on our current atomic environments, and it adjusts to the current atomic environments. So how would we define such an adaptive cutoff? So the first observation is the smaller is the cutoff, the better. The smaller is the cutoff, the less is the number of neighbors. So the less is the number of coordinate system used by our symmetrization protocol, and thus the higher is the computational efficiency. The second observation is that there should be at least one good pair of neighbors inside this adaptive cutoff. In order for our symmetrization protocol to be working, there should be at least one well-defined coordinate system. So summing all this together, it makes a lot of sense to define our adaptive cutoff to be something like second minimum of all the distances from central atom to all the neighbors. Of course, we cannot define our adaptive cutoff in such a simple manner just to be exactly the second minimum. So basically, it is more complicated than that. First of all, our adaptive cutoff should be strictly larger than the second minimum. It should be smooth, contrary to the plain second minimum. Second minimum is a not smooth function. And also there are corner cases, such as if the closest pair of items form a collinear triplet with the central one, our cutoff radius should smoothly and dynamically adjust to this corner case and become large enough to encompass also the third neighbor, and so on. Incorporating all these requirements, we produced some approximation for a second minimum, such some smart second minimum. And let me illustrate you how it works. So this slide illustrates the behavior of our adaptive cutoff. So the left panel is basically the general simulation. So we have central atom, we have 7 neighbors. So in total, there are 7 multiplied by 6, 42 coordinate system. But for current moment of the time, there are only 3 neighbors inside our cutoff radius. So currently, our symmetrization method uses only a 6 coordinate system out of 42, which is quite an improvement. And so atoms which are outside the cutoff are half transparent. Methods which are inside the cutoff and thus used by symmetrization protocol are fully colored. So let's see how it works over time. So as you can see, our cutoff radius dynamically adjusts to a given geometry. And overall, it results that the average, by average, I mean just integral over time, our symmetrization method uses just 9.7 coordinate system out of 42, which is quite an improvement. Our animations on these slides actually illustrate the mentioned corner cases, namely the behavior of our adaptive cutoff radius when the 2 closest neighbors appear to form a collinear triplet with the central atom. So as you can see, when this happens, for instance, now the closest pair of neighbors form nearly a collinear triplet with a central atom. So our adaptive cutoff dynamically and smoothly adjusts to become large enough to encompass the third closest neighbor. And so there is always at least one well-defined coordinate system inside our adaptive cutoff. And the final animation here illustrates a more complicated corner case, the situation when 3 closest neighbors become collinear. In this case, our adaptive cutoff becomes large enough to encompass the 4th neighbors. In general, this holds for any k if k closest neighbors are collinear. Our adaptive cutoffs will become large enough to encompass the k plus 1. So before I go next, I actually have to tell you something about the actual definition about our smart second minimum. And actually, I cannot present you the actual definition, the full math behind this construction, because it's just too cumbersome and it is barely possible to fit it within a presentation. But the good news is that I can illustrate you the main idea of this construction. And I can illustrate you the main idea of this construction on a much simpler problem. Instead of analyzing the fancy-pantsy approximation for a second minimum, I can illustrate you the discuss the well-known approximation just for a minimum. Actually, the smooth approximation for a minimum is given by this well-known construction. So basically, this is a weighted average of our points. Their weights are given by this exponent. And this smooth approximation for a minimum is parameterized by beta. And this beta controls the trade-off between smoothness and accuracy of approximation. So this trade-off is illustrated on this plot. So as you can see, there is a green line, there is a blue line. And as you can see, both green line and blue lines are smooth, but despite this fact, the real minimum between the two, the dotted black line is not smooth. It has a cusp here. It is not differentiable here. The smooth approximation to a minimum, the green line is smooth. It is differentiable here. And we can compare the behavior of these smooth approximations for different betas. For small beta, for medium beta, and for large beta. As you can see, when beta is small, our smooth approximation for minimum is quite off. Namely, it's quite far from the real minimum, so the accuracy is not really good. When we increase the beta, our approximation becomes more close to the real minimum. And finally, when the beta is very large, our approximation is very, very close to the real minimum. But unfortunately, there is a price to pay. Namely, the larger is the beta, the less smooth is the approximation, which is illustrated by the second derivative. So the y scale for all these subplots is exactly the same. And you can see that for small beta, the second derivative here is not really large. But when we increase the beta, the second derivative becomes progressively larger and larger. And so the larger is the better, the less is smoothness of the approximation. So now, actually, why I presented you all this? I presented you all this because our construction for our cutoff radius, which is actually some smooth approximation for a second minimum, is built upon the very same ideas, and it is also parameterized by some beta, and this beta plays exactly the same role. So it also represents the trade-off between smoothness and accuracy of approximation. So now we are ready actually to see how this works in practice. And so there are, once again, the free simulations. Actually, no, this is the one simulation, namely the arrangements of all the atoms here, here, and here is exactly the same for all the moments of the time. And the only difference between these simulations is the value of beta. Here, beta is 10, which is quite small. Here, beta is medium, like 50, and here, beta is 200, like really, really large. So here, beta is quite small. So our approximation for a second minimum is quite off. So our adaptive cutoff is much larger than the real second minimum. And so there are as much as 5 atoms inside the cutoff sphere. And thus, for the current moment of the time, our symmetrization protocol uses 20 coordinate systems. And thus, there are 20 non-zero weights. This panel is just a histogram of all the weights associated with all the coordinate system. And currently, only 20 of them are non-zeros. Here, basically, beta is larger, thus our cutoff radius is actually closer to the second minimum. It is smaller. Thus, there are only 3 neighbors inside our cutoff radius. And thus, for this moment of the time, our symmetrization protocol uses 6 coordinate system, which is beta. And finally, for the largest value of the beta, our symmetrization protocol, so for the largest values of the beta, our cutoff radius is really, really close to the real value of the second minimum. Thus, there are only two neighbors inside the cutoff radius. And for current moment of the time, our symmetrization method uses only two coordinate systems. Now let's see how this situation evolves over the time. Okay, it evolves somehow. Probably it is not necessary to look to the whole 30 seconds. Probably we can stop here. So overall, this situation results in that the average number of coordinate system used by symmetrization protocol for beta equals to 10 is about 13. The average number of coordinate system for beta equals to for beta of 50 is about 4.5, and for very large beta of 200, our symmetrization protocol uses as small as 2.5 coordinate systems on average. So as you can see, the larger beta implies a more accurate approximation of the second minimum, which in turn leads to the decreased computational cost. So immediate question here is why did we stop at beta equals to 200? Maybe we can select beta to be like 1,000, 1 million, 1 billion, maybe, I don't know, 1 Google. And maybe we can just keep increasing the beta and thus keep decreasing and decreasing the computational cost. Unfortunately, this is not the good idea, and there is a price to pay. And my next slide illustrates this price. So this is once again some simulation, and once again arrangements of all the atoms for the simulation on top. And for the simulation of bottom is exactly the same for all the moments of the time. And the only difference between these two animations is the value of beta. Here beta is small, and here beta is large. So what happens here is that over the simulation, the green atom goes away from the central atom, and the red atom goes towards the central atom. So initially, the only pair of neighbors inside the cutoffs is the gray and green one. Thus, only two coordinate systems were active, these ones. And but when the simulation continues, the red atoms enters the cutoff sphere. So now there are 3 atoms inside the cutoff sphere, and now in total our symmetrization method uses 6 coordinate system, these ones. Finally, the green atoms goes completely away from the our atomic environment, and thus at the end of the simulation, our symmetrization protocol once again uses only 1 pair of neighbors, the gray and red one. And thus, at the end of the simulation, once again, only 2 coordinate systems are active, these ones. So now, when I have explained to you what is happening and all the plot and the meaning of all the subplots, we can watch the simulation once again and contrast the behavior for small beta and for the large beta. So what we can see is that when beta is small, the transition from the green coordinate systems to red coordinate system is very slow and very smooth. This is especially clear if you look at the static plot. So the transition happens about 0.5 units of a time. So it's really like gradual and smooth. If beta is large, the transition from green coordinate systems to red coordinate system is quite fast, as which is especially clear on the static plot, and thus the transition is not really smooth. So before I can just conclude that there is trade-off between computational efficiency and smoothness, I want to exactly define what I mean here by smoothness, because smoothness is an ambiguous word. Namely, at least two things can be understood by smoothness. Actually, the first definition of smoothness is rigorous mathematical smoothness. Namely, we call a function to be smooth if it is k times continuously differentiable. The k depends on the context. And but there is also the second definition of smoothness, which is physical or common sense smoothness. Namely, it measures how fast our function oscillates, or equivalently, how large are the associated second derivatives. So mathematical smoothness is a discrete notion. So function is either smooth, either not smooth. Namely, this function is not smooth because it's not differentiable here. All the other functions are smooth in a mathematical rigorous sense. But from the physical or common sense smoothness, there are gray scales. Namely, this function we call not smooth at all. This function we call rather not smooth. This function we call something in between. This function we'll call rather smooth. And this function we call perfectly smooth. So now we can come back to our trade-off between smoothness and computational efficiency. So parameters of symmetrization protocol, such as beta, actually define the trade-off between computational efficiency and physical or common sense smoothness. The mathematical smoothness is the rigorous mathematical smoothness is never compromised. So that is pretty much everything what I intended to tell about the symmetrization protocol. I just want to point you to our things, which are too cumbersome to squeeze into the presentation. First of all, you're welcome to see the Appendix F of our paper to see the actual definition, some gigantic formulas of our smart second minimum. There is also one absolutely pathological corner case. Namely, it might happen that absolutely all the atoms in atomic environment are exactly collinear. So we cannot define even a single coordinate system. So in this case, we are pretty much screwed, but there is some way around. And there are few other things, such as application to message passing schemes. Also, our symmetrization protocol supports producing not only invariant properties, it also supports covariant properties, such as vectorial dipole moments and so on. So now I want just to relate the presented method to our methods which enforce rotational equivariance a posteriori developed in the community. So the first of all, there is already mentioned DeepMD, which constructs the single coordinate system by a pair of closest neighbors. And I have already shown you that this definition of a single coordinate system is not smooth. The second very nice paper is frame average and framework. And idea here is that we can construct a local coordinate system as eigenvectors of a covariance matrix. And for such a construction, there is once again exactly the same problem. So eigenvectors of covariance matrix sometimes also jumps in a discontinuous manner. Namely, they are not well defined when eigenvectors of this covariance matrix, eigenvalues of this covariance matrix are degenerate. The final paper I wanted to mention it is this one, equivariance with learned canonicalization functions. And idea here is that we introduce some auxiliary small equivariant neural network that predicts some raw vectors for our input three-dimensional point clouds. And next, we obtain a coordinate system from these raw vectors by Gram-Schmidt articulation. And there is, once again, the same problem. So such a definition of coordinate system might still introduce some discontinuous jumps, namely when the mentioned raw vectors are collinear with each other. Just so summing this up, these methods of a posteriori symmetrization developed by the community, all of them sacrifice smoothness. All of them sacrifice smoothness, which is not really nice, because smoothness is also very nice property of a model, and it is required for a model to be used in practical simulations. To the best of our knowledge, our method was the first who did the a posteriori rotational symmetrization while preserving the smoothness of a backbone architecture. And finally, I want to mention another paper which were out after our paper. And this is equivariant frames and the impossibility of continuous canonicalization. It has multiple contributions. For instance, it generalizes this idea of weighted averaging from only one group, the rotation group, and only one type of input object from the three-dimensional point clouds to multiple groups and multiple types of input objects, namely, for instance, to point clouds and d dimensions. The second result of this paper, which I like the most and which is absolutely fascinating, is very complementary to all this story. It is the impossibility of continuous canonicalization. So I just reviewed a few ways how one can construct a coordinate system given a three-dimensional point clouds. And for all these constructions, there are sometimes discontinuous jumps. So this immediately raises the question, maybe we just need to try harder, maybe we just need to think a bit more, and maybe we eventually will come up with some absolutely genius construction of a smooth single coordinate system. And this result, the impossibility of continuous canonicalization, states that no, it is not possible, and there is a formal proof for this. Thus, doing the ensembling, like I presented to you today, is the only way to go if we want to preserve smoothness. This was not the complete review of the related work. For a complete review, I advise the listeners to go to the section Unconstrained Geometry Graph Neural Network of Hitchhiker Guide to Geometry Graph Neural Networks paper. It is really nice. I highly recommend it. So now I can go to the second part of my talk. Actually, it will be quite short, I promise. And this talk about our unconstrained neural network about point H transformer. So before I actually proceed to this part, let's take a step back and think about the situation from the very general point of view. So from the very general point of view, atomistic machine learning has been dominated by models which intrinsically incorporate rotational equivariance because of two main beliefs. The first belief is that rotational equivariance per se is a must-have property for practical simulations. And this concern I addressed in the previous part of my talk about the symmetrization scheme. The second concern is that it is believed that rotational equivariance is a valuable, or I can even say must-have, inductive bias, which is necessary to incorporate into a model to get a good accuracy and good generalizability. So this part of my talk addresses the second concern, and basically I introduce a model which do not incorporate rotational equivariance intrinsically into the architecture, but it performs really well, and actually it achieves state-of-the-art performance on multiple benchmark data sets covering both bulk materials and molecules. So the architecture is illustrated here. So actually, I'm not sure. Maybe I am quite short on time. Maybe Hannes, what do you think? Is it worth actually to present the architecture, or I can just skip it?
I wouldn't go into this diagram now.
Okay, so probably I skip the architecture, I skip main hyperparameters, I skip properties, and I can just go to the results. So on this slide, you can see some ablation studies, namely the performance of our model depending on the choice of hyperparameters. And I do not really want to delve into the nature of these ablation studies. What is really important here is that I compare the performance of our architecture with an equip. And as you can see, our model performs with proper hypers, the equip. It outperforms, and it outperforms by quite a margin. So the dataset is a liquid water dataset, and yeah. The next benchmark that I want to present is the performance of our model on the dataset of randomly displaced CH4 configurations. And on this slide, you can see so-called learning curves. It means that on the horizontal axis, you can see the number of training configurations. On the vertical axis, there is the root mean squared error on the test subset. And as you can see, our model not only outperforms all the other models in the data-rich regime, but it also improves faster with the increase of the number of training configurations compared to the other models. So the slope of our learning curves is better compared to our models. And probably I can just very briefly go over our models, which are compared with PET. These are Wigner kernels. This one is basically the classical gap potential, basically the kernel regression based on power spectrum. This is nice. The NN, the yellow line, is basically a shallow multi-layered perceptron based on concatenation of power spectrum and B spectrum. And the blue line is basically the ACE, the linear regression based on the ACE features with very carefully selected physical preconditioning with very carefully selected physical inductive bias. And because of this model actually is the best of all the others. It performs really well in the data scarce regime. But as the number of training configuration increases, we observe that PET eventually outperforms these models. So there is an intersection. The next slide is basically exactly the same data set, but now, contrary to the previous case, where the fitting was done only on energies. Now fitting is done on both energies and forces. So half transparent lines are the lines from the previous slides, just for a comparison. So essentially here I compare PET, the black line, with only one hour method with the RIAN. RIAN is a free body invariant graph neural network. And as you can observe, there is once again exactly the same story. So PET outperforms RIAN in the data-rich regime, and it improves faster with the increase of training configurations compared to this hour model. The next slide is once again the learning curves, and now I investigate the performance of PET not for invariant targets such as potential energy. Instead, I investigate the performance of PET for a covariant target, namely for a vectorial dipole moment. And as you can see, our unconstrained PET that does not intrinsically incorporate any sort of rotational equivariance not only works also super good for a vectorial target such as dipole moments, but moreover, it achieves state-of-the-art, outperforming many other methods. The final slide with the benchmarks is this table. So first of all, I want to draw your attention that PET outperforms such models as GEMNet and DAMNet++ on the call dataset. So as you can see, the improvement in energies is quite dramatic, and simultaneously there is like teeny improvement in forces. So the reason for this is that the primary training objective for both DAMNet and GEMNet were forces, which explains so massive improvement in energies, but PET simultaneously manages to also improve a bit the performance in forces, like 23 versus 26. The next, I want to draw your attention to the comparison with MACE on the high temperature multi-element dataset. And as you can see here, the situation is much more even. So MACE is really, really good model. MACE actually outperforms PET on this dataset, but the difference in performance is quite neglectable. The performance is really, really close. And also, if we do an ensemble, so what I mean is that we fitted 5 independent PET models for the same train val test split with different random seeds. And if we simply average the predictions of the ensemble, we eventually outperform MACE in forces. The other two columns represents the comparison with some old school models. This one is the variation of Fresnel neural networks, the magnetic variation of it. This model is basically some Frankenstein monster. So it is simultaneously like old school shallow MLP based on power spectrum, and it combines it with modern style embeddings. And as you can see, PET outperforms such old school models quite dramatically, like 5, here it's 5 times, 3 times, also like 3 times and 5 times. So I have finished with the benchmarks. So basically, PET is available online, so you can basically enjoy this model with so good accuracy for your own applications. You can fit the model yourself. Actually, the current state of the code is, of course, not so good as for such established models as Schnitt-Park, Nequib, MACE, Allegra, but the current state of the code is much better compared to what I had at the moment of new RIP submission. So you are really welcome to give it a try. So now I can go to the last slide of my presentation. So first of all, I have to say that I have presented you a general method that enforces rotational equivariance for any backbone architecture while preserving all the other physical constraints and smoothness in particular. It means that the enlarged design space, I mean here not only the functional forms at layers that preserve equivariance. So this enlarged design space is now available for atomistic machine learning. The excellent performance of PET clearly illustrates that it is indeed beneficial to use these additional layers. And if we do not exactly incorporate rotational equivariance into a model, it is possible to achieve very good performance. Independently, the same was observed by such models as ForceNet and spherical channel networks. In particular, ForceNet just explicitly states in the abstract that if we relax rigorous rotational equivariance, it is really beneficial for the trade-off between computational efficiency and expressivity for a model. See more details and see more related work in the already mentioned section of this excellent review, Hitchhiker's Guide to Geometric Graph Neural Networks. And the last point which I want to make, that there is a massive empirical evidence that unconstrained models are more efficient, which comes from other domains, including three-dimensional point clouds. And illustration here is the ModelNet 40 dataset. This is probably one of the most popular benchmarks for generic point clouds, and it consists of objects such as a plane or armchair, consisting of like three-dimensional point clouds. And the task for this dataset is classification tasks. So given an object such as this one or this one, the machine learning model is asked to predict if this is a plane or this is an armchair. So we can observe that if we rotate our plane in space, it doesn't turn into armchair, and vice versa. If we rotate our armchair in space, it doesn't turn into a plane. So in other words, it means that our ground truth target is invariant with respect to rotations. And despite this fact, despite the fact that a ground truth target is invariant with respect to rotations, the leaderboard for this benchmark is dominated by unconstrained models, which are not rigorously invariant with respect to rotations, such as the ones in our field of atomistic machine learning. And this is a strong empirical argument that probably unconstrained models might be more efficient, and it is at least worth to give them a try. So that was the last point I wanted to make. I want to thank everyone for coming here and for your attention. That's all.
Okay, thank you, Sergey. I had a question about, like, if we now have these adaptively shrinking and increasing fields of horizon in which we put or in which we say that we produce what do we call it, local frames or something like that, then yeah, isn't there like some sort of implicit reasoning that our neural network now has to do that should be kind of hard of figuring out when an additional term comes in, and like when an additional term by an additional frame comes in, and this should make learning kind of harder?
This is a very good question. Also, the first thing I have to say is how we apply our symmetrization protocol. So we do not turn it on during training at all. Instead, during training, we fit our model with just random rotational augmentations. And next, we turn on our symmetrization protocol only during the inference. So
Okay.
this immediately raises the question, so what is the accuracy of the symmetrized model in relation to the accuracy of the unsymmetrized model? So the functional form of symmetrization protocol is the weighted average of the prediction of our initial backbone architecture for several rotations. So it means that the functional form of our symmetrization methods is some ensemble of our initial backbone architecture. And so we can think of symmetrization protocol as of some sort of test augmentation, and thus we can expect that the accuracy of the symmetrized model in the direct target in energies should be a bit better compared to the accuracy of the initial backbone architecture. It's just exactly the same as a well-known strategy to improve accuracy by an epsilon on some Kaggle competitions. You just do augmentations on the test dataset.
Yeah. Okay.
So basically, in case of the forces, the situation is more complicated, because when we switch from one coordinate system to another coordinate system, when we differentiate this functional form, there are additional terms which are associated with the derivatives of the weights of the symmetrization protocol with respect to positions of the points. So with the forces, situation is more complicated, and actually the error in forces of a symmetrized model might be larger compared to the error in forces of initial backbone architecture without symmetrization. And I also have an appendix in my paper discussing this. So probably I can find it and point it to you. It's just a second.
I think it's fine. I'm not planning to look at it.
Yes.
Okay. Good. Another thing I was thinking about is I think at some point you pointed out some theorem that we cannot get for general point clouds, some formulation that is fully locally equivariant or something like that. Can you maybe go back to this slide where you pull that up, if you know what I mean? I think you cite a paper that shows something like that.
Yes, it is this paper.
Yeah, okay. And then if we think about molecules, is it maybe the case that we basically can, or could it be the case that just now is no longer a general point cloud, and that there might be some way to have a continuous canonicalization that isn't that this no longer holds?
Yeah, it's possible. For instance, if we have some simulation of some molecule, and let's say the chemical bonds are never dissociated, in this case, probably we can define this local, or not local, maybe even global coordinate system, given just some fixed sets of atoms. And since the chemical bonds are never dissociated, it is fine. We just never face the problematic regions where we need transitions.